Hello everyone, welcome to this video on oxidation states exhibited by the lanthanons. Lanthanons are the 4F series elements and they are mainly electropositive in nature. That is, they have a tendency to donate their valence electrons. Oxidation state refers to the charge that is developed on an atom after electrons are donated, accepted or shared during bond formation. So in this video, we are going to see about the common oxidation states and the anomalous oxidation states exhibited by the lanthanons. So let's start. So we will start by just briefly quickly having a look at the position of the lanthanons in the periodic table. So they are elements of group 3 and the 6th period, and these elements, except for lanthanon, the remaining elements are placed separately in the F block and they form what is known as the 4F series. This is a table that shows the observed electronic configuration of the lanthanons, starting from lanthanum to lutetium. So these elements, their electronic configuration is characterized by the filling up of the 4F level, that is the N-2F level. The general electronic configuration of the lanthanons can be written as N-2F 1 to 13, N-1D 0 to 1 and Ns2. To be more specific for the lanthanons, the outermost shell is a 6 shell and the s orbital gets occupied. N-1, that is the 5D level, can get occupied by 0 to 1 electrons, and N-2F, that is the 4F level, can have 1 to 13 electrons. So lanthanons are basically elements which are having incompletely filled 4F level. That is, the number of electrons in the 4F level can range from 1 to 13. In spite of this restriction, lanthanum and lutetium, lanthanum which does not have even a single 4F electron, and lutetium which is completely filled at the 4F level, they are included in the study of lanthanons because of the similarities in the properties that they exhibit with the other lanthanons. So now let's move on to the oxidation state. So as I've already mentioned, this is the general configuration that can be written for the lanthanons. It is seen that all the lanthanons exhibit a common oxidation state of +3. Now this +3 oxidation state is attained by the loss of 2 electrons from the 6s level and 1 electron either from the 5D level or from the 4F level. So let us have a look at some elements. For example, lanthanum, atomic number 57, its outermost configuration, observed configuration, is 6s2 5d1. So it exhibits the +3 oxidation state by the loss of 2 electrons from the 6s level and 1 electron from the 5d level. In case of cerium, atomic number 58, where the outermost electronic configuration is 6s2 4f2, the +3 oxidation state is attained by the loss of 2 electrons from the 6s level and 1 electron from the 4f level. Now, apart from the common oxidation state of +3, which is exhibited by all the lanthanons, there are some lanthanons which exhibit what is known as anomalous oxidation states, which are oxidation states apart from +3. For example, cerium exhibits +3 as well as +4 oxidation state. So the +4 oxidation state is referred to as an anomalous oxidation state for cerium. Now let us see how this oxidation state can be explained. Cerium, the outermost configuration is 6s2 4f2. In +3 oxidation state, after the loss of 3 electrons, 2 from the 6s level and 1 from the 4f level, cerium in +3 has a configuration of 6s0 4f1. But in the +4 oxidation state, the configuration becomes 6s0 4f0. That is, cerium is basically attaining the configuration of noble gas xenon. Therefore, your +4 oxidation state is more stable than the +3 oxidation state, as cerium in the +4 oxidation state is attaining the configuration of a noble gas. Europium is another element which exhibits, apart from +3, another oxidation state, that is +2. So let us again have a look at the configuration of europium. It is 6s2 4f7. In plus 3, the configuration becomes 6s0 4f6. 3 electrons are lost, 2 from the 6s level and 1 from the 4f level. But if you see the oxidation state of plus 2, europium acquires a configuration of 6s0 4f7. 4f is exactly half filled. So the plus 2 oxidation state obviously is going to be more stable than plus 3, because in plus 2, europium is having the extra stability of exactly half filled 4f7 configuration. Terbium also exhibits two oxidation states. One is plus 3, that is a common oxidation state, and the other one is plus 4. Configuration of terbium is 6s2 4f9. In plus 3, after the loss of 3 electrons, the configuration becomes 4f8. Apart from plus 3, terbium is also exhibiting plus 4, where the configuration becomes 6s0 4f7 after the loss of 4 electrons. Obviously, the plus 4 oxidation state is more stable than plus 3, because in the plus 4 oxidation state, the terbium is having exactly half filled 4f7 configuration, which is having extra stability. Ytterbium exhibits plus 3 as well as plus 2 oxidation states. Ytterbium, the configuration of ytterbium is 6s2 4f14. So in plus 3 oxidation state, that is the common oxidation state, the configuration is 4f13. But in plus 2, the configuration becomes 6s0 4f14. Plus 2 is more stable than plus 3, because ytterbium in plus 2 is having completely filled 4f level, which is obviously going to be more stable than the 4f13 configuration that it will have in the plus 3 oxidation state. Now there are some elements where the anomalous oxidation state cannot be explained on the basis of an extra stable electronic configuration. Let's see this element neodymium, atomic number 60, and its configuration is 4f46s2. Like all lanthanons, it exhibits plus 3 oxidation state, where the configuration becomes plus 4f3 after the loss of 3 electrons. But apart from plus 3, neodymium also exhibits plus 2 and plus 4. But if you look at the configuration of neodymium in plus 2, after the loss of these 2 electrons, the configuration becomes 4f4. Or in the plus 4 oxidation state, where after the loss of 4 electrons, the configuration becomes 4f2. Neither of these two oxidation states can be explained on the basis of a more stable electronic configuration. We cannot say that 4f2 or 4f4 configuration is more stable than 4f3. So it's obvious that electronic configuration is not the only factor that decides the stability of oxidation states. There are other elements like samarium, which exhibits plus 2, praseodymium, which exhibits plus 4, thulium plus 2, dysprosium plus 4. Now these oxidation states cannot be explained on the basis of a more stable electronic configuration. So such oxidation states where we cannot give an explanation on the basis of the electronic configuration, such anomalous oxidation states are explained by different thermodynamic and kinetic data. So this is a table that is basically showing the oxidation states exhibited by all the lanthanons, and as you can see, all the lanthanons are exhibiting plus 3, and apart from that there are some lanthanons which exhibit plus 2 and plus 4 oxidation state. So for some lanthanons we can exhibit these oxidation states, we can explain these oxidation states on the basis of their configuration, but for some lanthanons it is obvious that there are other thermodynamic and kinetic factors that play a role in deciding the stability of oxidation states. Thank you for watching this video.